Thank you. Hello. Is that all right? Okay. Hello, everyone. I'm Kai. I'm from the machine learning group of University of Cambridge, and today I'm going to talk about this probabilistic programming project named Turing I'm currently working on. This Turing project was originally developed by Hong, and we are both supervised by Professor Zubin Germany. So here is the outline of my talk. So I will briefly introduce what is probabilistic programming, and then I will talk about our motivation of choosing Julia as our language to do the project. Then I will introduce some of the key features of Turing. And after that, I will go into a bit deeper about how Turing works. Then I will give you a live demo, and if time allows, I will give you another. And finally, some questions. Okay, so what is probabilistic programming? So generally speaking, probabilistic programming is just general purpose programming with some intrinsic support of non-deterministic statements. So by non-deterministic statements, the most common one is a rand function, which will give you a random number from the uniform distribution. So programming language like that are called probabilistic programming languages, which is short for PPLs. So one of the main application of probabilistic programming languages is probabilistic modeling, which is actually a popular field of machine learning. So, yeah. And there are basically two types of PPLs. So one is so-called standalone PPLs. They have their own syntax, their modeling language, and they have their own compiler so that they will translate their model into a code to do inference. Examples are like bugs and Stan. And there are another type of PPLs are so-called embedded in PPLs. So they don't have their own original language, but they embedded their system in a master language. For example, we have probabilistic C in C, Anglican in Clojure, Edward in Python, Web PPL in JavaScript, and Turing in Julia. So on the right-hand side is a typical model with both mathematical expression and their code in Turing. So this is basically a simple Gaussian model with conjugate priors. So on the top is the mathematical expression, and at the bottom is the Julia code. So as you can see, this the modeling syntax in Turing is very intuitive. Basically, you just write the mathematical expression into as a Julia code, and Turing will handle it for you. Okay, let's look a bit close to this piece of code. So I mentioned probabilistic programming is about non-deterministic. So where the non-deterministic thing happens is about this from these distributions in the model. So basically, you can see there are inverse gamma distributions. There's a normal distribution. So when you run this program, it will generate some random number from the corresponding distribution. So this is a non-deterministic. So about language, we call Turing a probabilistic programming language because we do have our some syntax like this tilde notation, and we achieve this by using the metaprogramming technique in Julia. We have basically two macros in Turing. This model macro will wrap a function definition, and inside function definition, you can also use this tilde notation to say a variable is distributed from a distribution. And so in Turing, you can define model like this, and then you can do machine learning. So to be more specific, you can do Bayesian inference by sampling methods. So here, after defining this model, you can feed some data into the model and get a model function. And then you can say, I want run a particle filtering algorithm. And then you can simply say, please sample some model parameters from this model using this algorithm. So there is a typo, there should be 1, 2. And similarly, you can just try another sampling algorithm, for example, Hamiltonian Monte Carlo, and you can just run almost the same code to do a sampling. And by sampling, basically you are done the Bayesian inference. So, okay, so why we choose Julia to implement Turing? So the first reason is that Julia has a rich collection of statistical libraries. So we are using some functions from the stats fun, and we are highly dependent on the distribution package because probabilistic modeling is basically using lots of distributions. And we also use the Mamba package to summarize the MCMC chain we produced. And also, metaprogramming is another reason. So Julia Turing indeed embedded in Julia, but it still has some of its own sampling syntax, the tilde notation. So it is enabled by the metaprogramming. And also, we use the coroutine in Julia to implement the particle Gibbs, which is one of the main sampler in Turing. I will go into this a bit later. And also automatical differentiation. So forward diff package provides a very easy to use geotype. And we have some samplers which are using gradient information to run MCMC algorithm. And our HMC implementation uses AD from the forward diff package. So the next thing here is that the generic typing of Julia makes AD works all the way with all the differentiable distributions in the distribution package. So basically, if the model itself is differentiable, the AD will just get the gradient you want. So here are some key features of Turing. So first of all, Turing is a probabilistic programming framework. It allows you to do universal probabilistic programming with a very intuitive modeling interface embedded in Julia. So here by universal, I mean you can actually write any kind of Julia code inside the Turing the add model function. Yes. And the intuitive, you've already seen the probabilistic model defined in Turing is almost identical to its mathematical expression. And in terms of sampling method, we support models with both discrete variables and continuous variables. In terms of discrete variables, we have a set of particle filtering sampling method which allows you to sample discrete variables. And another good thing about particle filtering is that you can also have some kind of stochastic control flows inside your program. And we also have HMC samplers, which you can use it for differentiable distributions. And we recently released 2 new features, which is pretty cool. One of them is that Turing allows you to compose different samplers and allow them to run sampling in the same time in a Gibbs manner. I will show you an example soon. And also, Turing allows you to run MCMC for field iterations and stop the chain and resume it by the same or another samplers. So the good thing about this is that you can exploit different advantage of different samplers in different sampling phase. And there are some points we are currently working on. We are developing more novel samplers, and also we want to introduce some other inference methods except sampling. And also we are working on a very cool feature which basically a user-defined model is also a distribution, but a complex distribution. So why not allow user to write their user-defined model inside their defined program, so that we are going to allow user to compose their models as well. So here is a Gaussian mixture model right in Turing. So above is the mathematical expression, and below is the code. So I'm not going to describe the model because we will see it in the demo later. But the thing I want to mention here is that this model do have some discrete variables. For example, this z here. So basically, z is an integer. And in programming language, probabilistic programming language like Stan, you cannot sample discrete variables directly. If you come up with a model with discrete variables, you need to sit down, work some math to try to marginalize this discrete variable, and then you can run HMC on it. But in Turing, you can basically say, oh, there's a discrete variable. Okay, you can ask, you can say, I want a Gibbs sampler which compose a particle Gibbs sampler which will sample Z for you, and an HMC sampler which will sample another two variable for you. And then you can still run the inference by this line of code. So the nice thing here is that users do not need to do math in this case, and they don't need to care about how the inference, and they can focus on modeling. Here is the interface for resume or save and resume MCMC chain. So basically, you can say sample a model with some sampling algorithm and save the chain for me, and then you can ask another sampler to sample the model. But you can say, please resume from an existing chain. So how Turing works in bit detail is, so basically the key machine learning stuff here is Bayesian inference, which is a general framework for probabilistic modeling. And Turing automates this by using sampling algorithms. And the key Julia technique we use are coroutines, which used in the implementation of particle-based samplers, and AD, which is used in gradient-based samplers. About the system, we have four important key components. The model defined by the user, we've already seen that user can use a add model micro to define a Julia function as the model. And we also have seen that user can specify a sampler which with a specific sampling algorithm. And there is another hidden key data structure inside Turing, which is a so-called var info. Basically, it will handle the interaction between samplers and model, and user will not see it. And once the sampling is done, the samples returned to user are wrapped in a chain type, which is a subtype of the chain from the Mumba package, and then user can see statistics of their MCMC samples using a describe function. So this is a picture show how the internal of Turing works. Because of time, I'm not going to go into this in a bit more detail. And so I mentioned we use coroutines to implement our particle filtering algorithm. So the reason we do this is that in particle filtering, each particle can be represented using a coroutine. And by doing so, each particle is basically a live copy of the model, which is an ongoing execution of the model. Because of the nature of these algorithms, they frequently need to duplicate or kill particles, which is just stop or start a coroutine. And also, this algorithm will do the model evaluation sequentially for each observation, which means they don't want to run the function one time, but they want to stop and continue, which is also a good point of coroutine. And this implementation actually leads to the state-of-art particle filtering performance. And in Turing, the HMC, so basically the HMC algorithm only needs two information to run its MCMC chain, which is the unnormalized posterior of the model and the gradient. So in Turing, in Julia, basically we can just set the model variables with a forward diff dual type and execute the model program. Then the returned log joint the real part of the returned log joint will just be the unnormalized posterior, and the dual parts of the returned log joint will be the gradient. So then we got the information we need for HMC, then we can generate candidate samples and reject or accept them. Okay, it's time for some demos. So firstly, I'm going to load some packages I need, as well as generate some data point and use Gadfly to plot them. So the Gadfly is a bit slow for the first plot, so I'm going to continue. So basically, the data point I generate here is just some data generated from the random normal function, and I put some of them to the left and some of them to the right. Then you basically got two clusters of data. And I'm in probabilistic modeling, someone basically want a probabilistic model try to summarize this data, and I'm going to show this interactive process. And so we can start it from a very simple Gaussian model, which with an unknown mean. So this is a model in mathematical expression, and this is how it's written in Turing. So I'm going to define this model, and when the model is defined, you can specify the sampling algorithm you want and do the inference by this line of code. Once the inference done, as I mentioned before, we can use the describe function to check the statistics of the returned MCMC chain. So basically, you can see you have the mean or standard deviation of samples. So this is kind of boring, so I'm going to visualize this result. So as you can see, this very simple Gaussian model doesn't quite work well. It puts the density in somewhere which is not quite fit with the data point. So, and you can see the data point here even have very low probability in that model. So I'm trying to improve the model a bit by saying that, okay, I'm not going to fix the. So for the previous model, I fixed the variance, and here I'm saying that I don't want to fix the variance. I want to let the inference tell me what the suitable variance is. So here is the model, and basically I just need to change, add one line and change field place to translate this mathematical expression in Turing. And when I define model, still very simple. I just need to run this line to do the inference. And when the inference done, I will do the same visualization. So okay, it's a bit better now. At least the model doesn't put almost zero density in where the data points are, but it still doesn't fit the model quite well. So I'm going to try a even better model, which is a mixture of Gaussians. So basically, this is a mathematical expression, and this is the code. So as you can see, you are allowed to use this kind of for loop inside Turing to do the translation between mathematical expression to the code. And actually, you can use any kind of Julia code inside this program. So, and for those who don't know Gaussian mixture model, basically it says some data point can follow one mixture component, which is a Gaussian, and some data point can follow other component, which is also a Gaussian. And once you define the model like this, you can, as I mentioned, because there is a discrete variable, so we need to rewrite this sampling algorithm bit by saying that I want particle gibbs to sample a described variable here, and I can run this inference still by a single line of code. So once the inference is done, I can use the samples I collected to make a visualization, see how the result looks like. So hey, wow, we have a much better model now. So basically, this model captures there are two clusters, and it kind of put the mean of each mixture of its component to where the data points are. So this is the first demo. So the thing I want to emphasize here is that, as you can see, probabilistic modeling is a very interactive process. You have some data and you think about a model and you try to do inference to fit the model to data point, and you want to check the result, and you think another model which improves your idea. But without programming, you need to write the model which is very complex, and you need to find the inference algorithm to implement it, which is also very complex. But with probabilistic programming, you can kind of focus on just thinking which model is the best. You can focus on modeling instead of the detail of inference. So the second demo is a Bayesian neural net in Turing. So in the previous 2 days, you guys are already seeing some neural net demos. So I'm going to show you a Bayesian one. So first, still load some packages, and let me generate some synthesis data point. And because I'm plotting the data point here, so this section code is a bit slow. Let me continue first. So here I'm defining the sigmoid function I will use to implement the neural net. The neural network structure I'm going to work with is this, with two hidden layers here. And to write the forward path of this neural net in Julia is quite simple, which is just this function. Okay, so let's go back. So this is the synthesis data point I generated. Basically, there are labeled data in 2D dimension, and I want to use a neural net to work as a classifier to classify this data points correctly. And this here is the function for the main body of the neural network. Okay, once I define the forward path of this neural net, I can use Turing to do a Bayesian inference on it. So how it works is that I put a prior on each weight and bias of this neural network parameters. So here you can see I'm saying that each of these parameters are sampled from a normal distribution with some variance. And once after I say each parameter is from a normal distribution, I can say, oh, okay, just use this, use the model parameter to go a forward path of this neural nets. And once I get this result, I'm going to say what I observe is actually follows a Bernoulli distribution with the result of the neural nets as a parameter. So here I've defined the model, and similarly, you don't need to care about how the inference is done. You can still use this, use a very straightforward one line of code to run the inference. Here I'm using the Hamiltonian Monte Carlo sampler to generate this number of samples. So when the inference is done, I'm going to make some visualization of the result. So let me first convert the result into a format for visualization. And the first visualization I'm going to do is that I want to make a plot which uses the mean of the samples of variables I collected. So basically, when I'm doing that, I basically have a point estimate of the variables I have, and it will give you a decision boundary. So as you can see, it gives you a decision boundary which correctly classifies this point with different labels. But the thing here is that this boundary is a hard boundary. By hard, you will see what I mean soon. So instead of averaging the model parameters I have, I can actually do Bayesian inference because I have the samples from the posterior distribution. So the different thing from Bayesian inference and this visualization before is that in Bayesian inference, I average the prediction of neural nets for each samples, and I am going to visualize this as well. So this function basically says use each samples to make the forward pass of the neural nets and average the result for me. So here is the visualization. So I'm going to. So this bar means that how many samples I'm going to use to make the make this Bayesian prediction. So if I draw this bar smoothly, you can see how this sampling process is performed. So you can see the sampler generally become better and capture the two types of labels of data point. So as you can see here, this number of samples actually gives you a quite good prediction. And I mentioned just now, this boundary is a hard boundary, which just tells you on this side and this side are a blue point, and this side are green point. But the good thing about become Bayesian is that, of course, you still know which side is which color, but you also know that in between this boundary, you are not quite sure about which color the data point is. So compared with other optimization method, Bayesian approach also tells you the uncertainty about the prediction. So it is critical to have this property in in many cases. For example, if you only have few data point and you are really want to make the full use of your data point, it's better to deal things in this way. Okay, this is the end of this demo. And any questions?